Hi there, today we're going to be talking about simultaneous equations. So this is the 7th video in the quadratic series. We're going to start off with just a review of what we did before in IGCSE, which was solving simultaneous equations where both equations are linear, and then we're going to go on to look at what it looks like in the AS Maths syllabus. So the thing here is, solving simultaneous equations, you've got two different ways of doing it. So first of all, obviously what we're trying to do is find the values of x and y where both of these equations are true at the same time or simultaneously. So in the past you've got two straight lines and we're looking for the point of intersection. There's two methods that you need to know. So the first method of this that you need to know is the elimination method. That is, we're going to multiply one or both equations by a constant, which doesn't change them, so that either the x and or the y's are the same, the coefficient is the same. Adding and subtracting the equation will then eliminate one of the variables. So here, what I've done is I've multiplied the second equation by 2. So we get this equation here, which is exactly the same as this equation here. I've just multiplied everything by 2. Now by adding the first and the third equation, the y's are eliminated. And we can solve for x. X is 4. And then substitute x equals 4 back into either equation 1 or 2. I'll put it back into equation 2 here and found the value of y. Y is 2. So x equals 4 and y equals 2 is the point of intersection of those two. So that's elimination. The second method that's probably even more important is substitution. So what we're going to do is rearrange one of the equations and substitute it into the second. Now in this question here, it's already nicely done that y is the subject of the second equation. So substitution is the way to go here. We substitute in this y value here, x minus 2, and put it in there for that y value there. So we get this equation here. That's just substituting y is x minus 2 into the first equation. Okay, so when we do that, we then go on and solve that equation. We get x equals 3. Substitute that back into, obviously equation 2 is the easiest one to get y equals 1. So sometimes it's good to write it as a point, especially if there's some kind of geometrical analogy that we're looking for here. So the point 3, 1 is the point of intersection of those two there. Now that second method is the main method we're going to use when we solve equations now where one of them is linear, but one of them is something else. One of them is either a quadratic, a hyperbola, or a circle. So I'm going to show you the graphs of what this looks like. The first one is really common. So we want to find the point of intersection of this line and this curve. And here, both of them are y equals and y equals. So if y equals that and y equals that, then obviously this is equal to this. And that's my first step here. It's kind of the substitution method. So we end up with a quadratic equation. But this one here is in terms of x. So here's our quadratic equation. We rearrange so everything is on one side. We factorize. We could use the quadratic formula, but always try and factorize first in these questions, because often in this kind of question the quadratic will factorize. So we get two possible x values, which leads to two possible y values. Remember in the question y was 2x minus 1 up here. So we substitute in x equals -3 in there, get -7. Substitute 2 into that original equation and we get y equals 3. So that's our 2 points of intersection, -3, -7 and 2, 3. Here's what the graph looks like. We've got a parabola, we've got a line, and we've just found the point of intersection of the line and the parabola. In this example, we've got a line and a hyperbola, xy equals 8. The way we're going to solve this is rearrange the first equation here so we make y the subject. So that's the first thing there, y is 3x minus 2. Then substitute that into the equation of the hyperbola, xy equals 8. When we do that, we end up with a quadratic equation. So we expand the brackets out, we rearrange so everything is on one side equal to 0. And again, we try and factorize. And this one here factorizes nicely. We get two x values, substitute in to find the y values, and that gives us the point of intersection. And here's what it looks like. There's the hyperbola in red. There's our straight line, and we've found the coordinates of those points of intersection. In this question, we follow a really similar idea here. We've got a line, we've got a circle, and you don't need to know how to draw the circle. We can just see from the question here that we've got 2 points of intersection, and the technique that we're using here is very similar. Rearrange the equation of the line so y is the subject, and then substitute in that value for y into the equation of the circle, which again, with a bit of expanding and rearranging, leads us to a quadratic equation that factorizes nicely. We get the x values and then subsequently the y values and find those points of intersection. As I've said at the bottom here, it's unlikely that you have to use the quadratic formula for these. For these kinds of questions, quadratic equations can be factorized. So being able to factorize from here to here is a very good and important skill to have. More typically in the exam, you're going to find a question that asks you to use values of k like we did in the previous video, but in the context of solving two equations simultaneously. It's the discriminant that is the key in solving these questions. So we found out in the last video that the discriminant was the b squared minus 4ac part of the quadratic formula, and it tells us how many roots a quadratic equation has. Now, if we apply that to this situation where we're trying to find the number of points of intersection of a line and a parabola, if in trying to solve those two things simultaneously, the discriminant of the resulting quadratic equation is greater than 0, that means there's 2 points of intersection. If the discriminant is 0, there's 1 point, and that's the middle graph there. Or if the discriminant is less than 0, it means there's no points of intersection. So for example, we want to find the value of k such that that line is a tangent to the curve. So that line there, if we rearrange it, is just y equals 2x plus k. So it's a line that's got a gradient of 2 and a y-intercept of k. So you can see I've got lots of different lines there that have different values of k. For example, this one here is y equals 2x plus 2. Certainly it's going to have 2 points of intersection. So we're looking for the exact right value of k so that the line is a tangent. That is, that it just touches the curve at one exact point. That means that the discriminant here, when we try and solve these simultaneously, is going to be equal to 0. So let's do that. We rearrange the equation of the line. We solve them simultaneously, which means we make one equal to the other. So a bit of rearranging gets us to this thing here. So this is a quadratic equation where a is 1, the coefficient of the x squared, b is -4, and c is -1 minus k. That's a little bit tricky to see there, but that's a, b, and c. Value of k that we want is when the discriminant is 0. So b squared minus 4ac equals 0 is this step here. Expand out the brackets, 16 plus 4 plus 4k. Be very careful with the signs. Equals 0. Solve that for k, and we get k is equal to -5. So that's the unique value there where that line is a tangent to the curve. Last example here, for what values of k does that line intersect that curve at 2 points? So straight away, a curve and a line intersecting at 2 points means the discriminant is greater than 0. So we use a similar idea, just to give you an idea of the graph here. The red line is the quadratic, and that is when I change the value of k in this line. It's going to change the gradient of the line. The y-intercept is always the same, but you can see all the variations of the line here. So all the different values of k that are going to have us intersecting at 2 points. So I can see there's quite a few there, like this one. Let's draw this one. This one here that intersects at no points on the curve. But you can see all of these values of k intersecting here at 2 points on the curve. So it looks like we're going to have a range of values of k that are going to make this true. Okay, so the technique's the same. Rearrange the first equation, so y is the subject. Then substitute that into the second equation, y equals 2x squared plus x plus 1. I've multiplied everything by 2 here because I hate fractions, so it makes it a lot easier. Multiply everything by 2. Rearrange and get everything on one side. You can see that the coefficient of the x is 2 minus k. There's 2x terms there. And now for 2 points of intersection, the discriminant is greater than 0. So b squared minus 4ac is that step right there. Expand, and we have a quadratic inequality. So if you're not sure about those, I made a video about that. How to solve quadratic inequalities like this one here. So this one factorizes nicely. -2 and 6 of the roots were equal to 0. Here's the little graph here. And we want to know when is it greater than 0. So we're looking for the parts of the graph that are above the x-axis there. So we can see from the graph that it's the values less than -2 will be above the axis, and greater than 6 will be above the x-axis. So they're the values of k that we're looking for this question.